Welcome to week 11 of Algebra 1 with Mrs. Whybark. This week we will be talking some more about systems of linear equations, and we will be learning about the third method for solving them. This is called elimination. We will once again be using the Algebra School program, and the handout for this is labeled page 187. This two-page handout is available on the Moodle and will also be provided in class. You should follow along and fill this out as we go. Do show all your work for examples 1, 2, and 3 in order to receive credit for your notes. You may want to put those on the second page in order to have enough room to show all your steps.
Let's talk about elimination. We have used elimination in various ways in algebra to solve problems. Think about solving equations. For each equation, we eliminated some information so that we could determine a solution. Today, we will use elimination to solve systems of equations. Remember from our previous lesson that a solution to a system of equations of two variables is an ordered pair xy that satisfies all the equations in the system. In the previous lesson, we graphed the equations and found the solution. Today we will use our algebra skills to solve systems without graphing.
Let's look at a system of equations and find its solution algebraically by eliminating one of the variables.
This example is not included in your guided notes, but please follow along as they do an excellent example of showing how elimination works.
We have 5x plus 3y is equal to 19, and the opposite of x minus 3y is equal to negative 11. What do you notice about the coefficients of the y terms?
The coefficients of the y's are opposites.
That's right, Ferd. What could I do to the equations to eliminate the y terms?
If we added them together, we would eliminate the y's. But can we add equations together?
Yes, if equals are added to equals, the sums are equal, which is the transitive property of equality. Add the like terms in each equation and keep the equal sign in the same place. The result is 4x plus 0y is equal to 8. Remember that it is not necessary to write 0y, so 4x is equal to 8. We have eliminated the variable y.
Well, if 4x is equal to 8, x is equal to 2.
Good, Lizzie. Now, how do we find y?
If we know what x is, can't we just substitute that value in one of the equations and solve for y?
Exactly, Roxy.
But which equation should we use?
Use the equation that is easier to work with.
I like the first one. We know that x is equal to 2. Substitute 2 for x in the equation 5x plus 3y is equal to 19. That gives us 10 plus 3y is equal to 19. Subtract 10 from both sides of the equation. That gives us 3y is equal to 9. So y is equal to 3.
Okay. What is the solution to this system of equations?
The solution is the ordered pair 2, 3.
Good thinking, Ferd. You wrote the solution as an ordered pair xy.
But how can we be sure it's correct? Do I need to graph both equations and see if the graphs cross at the point 2, 3?
We can check the graph to see if the solution is correct, but there is another way. To check to see if an ordered pair is a solution to a system of equations, substitute the x and y values in both equations. If both become true statements, then the solution is correct.
So if I substitute 2 for x and 3 for y in the first equation, I get 5 times 2 plus 3 times 3 is equal to 19. That's the same as 10 plus 9 is equal to 19. Or 19 is equal to 19. That's true. And if I substitute 2 for x and 3 for y in the second equation, I get negative 2 minus 9 is equal to negative 11. Negative 2 minus 9 is equal to negative 11. So this equation is true as well. The solution is correct.
Look at this system of equations. 3x is equal to y plus 7. And 2x plus 4y is equal to 28.
Well, hold up. These equations are all messed up. The first equation has a variable on each side. And the second equation has both variables on one side. Can we go home?
We don't need to go home, Ferd. We need to rewrite the equations so that they are in the same form. Can I have some help?
Let's put the first equation in standard form. Then this system will look like the system in the previous example. Rewrite the first equation as 3x minus y is equal to 7.
Thank you, Newt. Now how would we solve this system?
Notice that all they did to the first equation was they subtracted y from both sides in order to have the x and y terms on the same side of the equal.
If only the coefficient of y in the first equation were negative 4 instead of negative 1, then we could add the equations and eliminate the y's.
How can we make it negative 4?
Multiply each side of the equation by 4. Oh yeah, just like we did before. I get it.
What do we get when we multiply both sides by 4?
This is something we have not yet done in class, but you need to know that it's okay to multiply an entire equation by a constant as long as you multiply every single term. So what they're doing here is they're going to multiply 4 times 3x and then 4 times negative y in order to get a negative 4y. That way the y terms will have opposite coefficients. And then they also have to multiply 4 on the other side of the equal sign.
The first equation becomes 12x minus 4y is equal to 28.
So now we can add the equations together to eliminate y, and then we solve just like before. 12x plus 2x is 14x. 28 plus 28 is 56. 14x is equal to 56. Divide both sides by 14. X is equal to 4.
Yeah. Now we can substitute x in the first equation and solve for y.
We should use the original first equation, Ferd.
Why?
2 reasons, Ferd. First, it is easier to work with. Second, it is a good idea to use the original equation just in case we made a mistake when we multiplied in the first step.
Okay. The original equation was 3x equals y plus 7. Substitute 4 for x and solve for y. 12 equals y plus 7. Subtract 7 from both sides of the equation. So, I get y is equal to 5. The solution is 4, 5. And, of course, the check would follow.
Good, Ferd. You can complete the check on your own. In question 1 of your guided notes, solve the system of equations using the elimination method.
For each of these 3 examples in your guided notes, I would like you to write down in detail all the steps required to solve the system. You may want to put this work on the bottom of the second page of your notes, as it will take a bit of space.
X minus 8y is equal to negative 1. 4x minus 8y is equal to 8.
The coefficients of the two y terms are the same. So I can multiply the second equation by negative 1 and add to eliminate the y's. The result is the equation negative 3x is equal to negative 9. Divide both sides of the equation by negative 3 to find that x is equal to 3. Use that value in the first equation to solve for y. Subtract 3 from both sides. And divide by -8. Y is equal to 1/2. The solution to this system of equations is 3/1/2. Check your solution by substituting 3/1/2 into the original system.
In question 2 of your guided notes, solve the system of equations using the elimination method. X plus 3y is equal to -20. The opposite of x plus y is equal to 0.
The coefficients of the two x terms are opposites. So I added the two equations to eliminate the x's. The result was the equation 4y is equal to -20. Divide both sides of the equation by 4 to find that y is equal to -5. Use that value in the second equation of the system of equations to solve for x. Add 5 to both sides. Divide both sides by -1. X is equal to -5. The solution to this system of equations is -5, -5.
Question 3 of your guided notes, solve the system of equations using the elimination method. 7x minus y is equal to 0. 2x plus 2y is equal to 0.
Multiply the first equation by 2 so that the coefficients of the y terms are opposites. Then add the two equations together to eliminate the y's. The result is the equation 16x is equal to 0. Divide both sides of the equation by 16 to find that x is equal to 0. Use that value in the original first equation to solve for y. Substitute 0 for x. Divide both sides by -1. Y is equal to 0. The solution to this system of equations is 0, 0.
To solve a system of equations using the elimination method, make sure the equations have like terms aligned in columns. For some systems of equations, it may be necessary to multiply one or both equations by different numbers to eliminate a variable. Remember that the goal is to make the coefficients of either x or y opposites. Add the equations to eliminate one of the variables. Solve for the remaining variable. Substitute that value into either of the original equations and solve for the other variable. Check the solution by making sure that the ordered pair satisfies both of the equations in the system.
Take a look at this system of equations. 6x plus 4y is equal to 5.
This example is not included in your guided notes, but I would like you to follow along as they do this example and complete the notes on the second page of your handout.
And 6x is equal to -4y. What do you notice about this system of equations?
The first equation is written in standard form, but the second is not.
Yes. Rewrite the second equation so that the variables are in the same order as the first equation.
The second equation can be rewritten as 6x plus 4y is equal to 0. Now the equations are in the same form. Can we add them?
No, we won't eliminate any variables. What can we do?
Multiply the second equation by -1, remember?
Then we can add. We get 0 is equal to 5. That's not true.
Notice that when they added these two equations, 6x plus negative 6x becomes 0, and 4y plus negative 4y is also 0. So what has happened is all of the variables have been eliminated, leaving us with 0 on the left equal to 5 on the right.
What are we going to do? When in doubt, graph it out. Let's look at the graph of this system. As you can see from the graph, the lines representing these equations are parallel. This system of equations has no solution. If you solve a system of equations by elimination and the result is a false statement containing no variables, the system of equations has no solution.
X plus 2y is equal to 3, and 2x plus 4y is equal to 6. How would we solve this system of equations?
Multiply the first equation by negative 2. That makes the coefficients of the x terms opposites.
This is scary. The coefficients of the y terms are also opposites.
What do we get when we add the equations?
0 is equal to 0. That's true. But all the variables are gone again. Now what?
Don't you remember, Roxy? When in doubt, graph it out.
Let's look at the graph of this system.
As you can see from the graph, the lines representing these equations are the same. This system has an infinite number of solutions, all the ordered pairs on the line.
This is an example of two equations actually representing the same line. So when you graph these two equations, you'll get the same line. And that means that every ordered pair on this line is a solution to both of these equations. Therefore, your answer is an infinite number of solutions. When you have completed your notes, the first page should look as follows. Notice on the second page is where I put all of the work used to solve the systems in examples 1, 2, and 3. Thank you for watching this Whybark production.